Hello and welcome to another video lesson in this course finite volume method using C++. And in the last video we implemented the solve equation method using the zip solver strongly implicit procedure. Okay, so now we are actually going to call this function, and before we call this function, let's just have a look at what we do need. So we need the vector field, which we have the u velocity. We need the source, which we also have. It's already been calculated in the equation class, and we need the solution object and number of iterations. Okay, so first of all we need the finite matrix. So just write finite matrix finite met and SU, which is the source term of the U momentum equation, and we can access this or get this by typing U equation and source relaxed, which is the final source term after modifications. Okay, and now we need the number of iterations for which we are going to solve, and this can be just one for the u and v momentum equations because they are fairly easy to solve. And now we're going to call this function by saying that it will return a vector field called utemp, which is an abbreviation for u temporary, and it will be called using the solve function, and we solve for u. Source term is su, solution object is solve, and iterations will be u iter. Okay, so we have done that. Now let's actually build and run. So now we have this print which says that u momentum in our iteration 0 and residual for the iteration is 0.014 and RSM is 1 because only one iteration has been done. Okay, and if you remember, for the pressure Poisson equation we need value called repu and repv. Let's actually go to the presentation and have a look at this. So for the pressure Poisson equation we need AP matrix U, so the reciprocal of the U momentum AP, and the reciprocal of the V momentum AP. So I'm going to call this in create finite matrices. We created AE, AW, ASN, which is actually not particularly useful, but APU and APV we have, and I'm just going to change the name to repu and repv. Okay, so the reciprocal of U momentum equation, which is the repu, will be equal to U equation rep, and we calculated in the equation CPP file. When we were doing the relax function, we calculated the rep value, the matrix, which is simply 1 divided by AP ij dot value. Okay, so we will just need to have this in order to prepare for the pressure Poisson equation, but we are not going to solve the pressure Poisson equation in this video. That's a whole other story, and we still have V momentum equation to implement. But that should be fairly easy now because everything has been set up. So now we're just going to implement the V momentum equation. So let's just say V momentum equation and say equation pointer V equation equals to new equation, and then the constructor definition in which we are going to call the finite volume operations, and this will simply be the diffusion term due to v velocity plus the diffusion, the convection term that arises due to v velocity as mass flux east and mass flux north, and the blending factor, which is we are using a factor of 1.0 plus the pressure gradient term, so FVM pressure gradient and P, and we need to give a direction. So in the U momentum equation we gave east direction. For the V momentum we will give north direction. Simply this means dpy. Okay, so now we have this equation set up, and then we can just copy this part and change everything to V equation. And for the V equation we call for the no wall shear and Y boundary conditions, and assemble the equation, relax the equation, and this will be the source term will be called SV, and of course V equation solve. The temporary field that we are going to return is called Vtemp, and it will take V SV and V eta, and rep V will be the reciprocal of V equation AP. Okay, so right, we got the U momentum equation, and we got the V momentum equation, and we got the rep U and rep V in order to prepare for the pressure Poisson equation. And let's build to see if there are any errors. Let's build and run. Okay, so the residual is 0 because we don't have any boundary values for the V momentum equation. One thing we could do is just print the matrix, the function that we commented out. Where is it? Print 2D matrix. Right. So let's actually print here cout initial values before entering the for loop, or before entering the iterations. So these are the initial values for the U velocity, and then we will print after solving and copying. I have actually missed one function, which is the copy function, so let's just call that function. So field opa dot copy internal field from U temp to U. Okay, and then also for the V, after solving, because the solve function returns this matrix V temp, and therefore we need to copy the value from V temp to the V velocity. Similarly for U, we copy from U temp to U velocity, and this only copies the internal field. Let's build and run. After printing this matrix, so let's copy this guy here after this, yeah, and let's say that this will be the U velocity updated after solve, and copy this and put it here and say this will be the V velocity updated after solve, and let's build and run. Alright, so at the before entering this for loop, the values were only at the boundary, but now it's being updated from to north side, and every internal cell has a value. But for the v velocity, there is no update because there are no boundary conditions that leads to any source terms, and the internal field and the boundary values at the first iteration was 0 for the v velocity. Okay, so let's see what we have done. Just a recap: we've implemented the u equation, updated the boundary conditions, assembled the equation, used under relaxation, and we've also called the solve function using the zip solver, and returned a temporary matrix called utemp, and we copied the internal field from utemp to u to update the u velocity, and we did similar all these setup for the v momentum equation as well. And in the next video we will be implementing the pressure Poisson equation, and in the video after that we will be updating the final UVP at cell center and writing the solution and visualizing. Right, thank you for watching.